to answer the question of, is a particular treatment is effective to a group of people? And there are many applications of causal inference. For example, in drug testing, people might want to know if a particular new drug is effective in treating a new disease. So there are two common approaches. One is experimental based, where you just gather a lot of people and you divide the group of people into two. You do the treatment on one of the two and you compare the effect between the two groups. This approach is sometimes expensive because you have to gather a large group of people. And also in some application, it might not be ethical when you have to do experiments on the people. So there's a second approach, which is observation-based, where you, based on the existing data, to study the causal effect. So causal discovery is an important part of the causal inference. It tried to answer the question for two variables, x and y. It tried to see if x causes y or y causes x, or there's no causality between the two variables. And we based on one structural causal model, which says that x causes y if we can model y as a function that takes x and some systematic noise as a parameters. And here you can see one example that the audience age might affect the probability that the ad is being clicked, and you have some systematic noise that also connect to the node. So because we are using the observational based approach, then when we have more data points, our prediction will get more accurate. But because you use more data points and sometimes you have collected from multiple parties, and the parties might have a conflicting interest, and they might not be willing to expose their data to you for causal discovery. So that's why we think that an MPC approach for causal discovery is necessary. So in our paper, we based on the additive noise model, which further simplify the structural causal models. So Hoyer et al. Proposed this model saying that x causes y if we can write y as the f of x plus the noise. So the noise here is only one linear factor and not the parameters of the function anymore. And here's a visualization of an example, which is y equal cosine of x plus e. And you see that the lower left showing the contour lines of the conditional probability y given x, and the mean, the average value change significantly when you change the value of x, while the similar effects do not being observed when you see the lower right. When you change y, the distribution have the mean doesn't change that much compared to the lower left. And this confirms that there's a causality between x and y. So Muji et al. Suggested that we can use a 4-step approach to causal discovery. Step 1 is you split your data into 2 data sets. Step 2 is on 1 data set, which is the blue point here. Which is the blue point here. You fit 2 regression models. One is for the x given y, and the other is for y given x. And step 3 is on the red points, the second data set. You compute the dependence score based on that data set and the 2 regression models that you got from step 2. And finally, you conclude if x causes y based on the dependence score. And the second step is the most expensive and also the most expensive in MPC setting as well. And it is the focus of the paper. So we found out that in causal discovery, people often use Gaussian process regression. And we found out that the complexity, as well as the number of nonlinear approximation you have to use is a lot. So we try to solve this problem by moving to support vector regression, especially the iterative approach, because it reduced the complexity. But we found out that the SMOSVR here has a really big number of if-else branches and early stopping. And when you try to do the secure training and secure inference, you need to run through the whole if-else branches for all the conditions. So we try to apply stochastic gradient descent, SGD, to reduce the number of branches. And lastly, we use budgeting for the storing of training samples. So instead of you have to store all of the training samples, now you only have to store a budget of data points, which reduce the communication cost. So here's an overview of our protocol. The first step, you have a bunch of data points that you want to train your regression model. Step 2 is you pick one data point and you compute the loss between the actual values and the predicted values of the original model. And in step 3, you use stochastic gradient descent on this one data point, and you try to minimize the loss, and you update your model. You also add this point to the budget, and when you repeat step 2 and 3 for multiple times, you will face the situation in step 4 where your budget is full and you want to add a new points. So what we do is that we choose the point which is the least significant. So we have a weight and we choose the point with the lowest weight and we remove it. We add the new point and we repeat 2 to 5 again, and we have the final fitted model. And as a result, we have an algorithm that has the best complexity and also that has no square root computation and no division. Also the smaller number of multiplications. So it is very friendly in the MPC setting. In the experiments, we use the Gaussian score for dependence score. As Gaussian score is the most MPC friendly, so we don't have any contribution here. We just choose the one that is most MPC friendly. This one only have 2 nonlinear evaluation. We benchmark our algorithm on 5 data sets from Muji to show the causal discovery performance. We also show the nonlinear function regression power of BSGDS-VR, and we compare BSGDS-VR to Gaussian process regression and SMOSVR. So in the first experiment, it's shown that we have the correct causality direction and also comparable mean square error to the benchmark algorithms. The second experiment confirms that BSGDS-VR has the nonlinear regression approximation power similar to SMOSVR. So we are fast, but we also accurate. So here's a very complicated algorithm figures where we want to make BSGDS-VR to be fully MPC. So for the machine learning algorithm, you still have some if-else and some part that is not trivially translate to MPC. So this is how we translate everything into MPC setting. And we train the MPC setting and benchmark the running time for training and communication cost and communication rounds. And you see that the runtime is like 4 times to 300 times faster compared to the benchmark algorithms. And also communication cost is much lower. And the rounds of communication is also lower. Same story for testing. We achieve the best testing time, best communication cost, and best communication round. Okay, let's conclude the talk. Thank you very much.
Any questions?
Yeah. Was it LAN numbers or?
Oh yes, so this is a LAN number. But I believe we also are the best in one number, given the communication cost and number of communication rounds, which is like much better compared to the benchmark.
Any other questions? Otherwise, let's thank the speaker again. Thank you so much.
Thank you.
You want me to move so that you can just sit here and write and speak?
No. The Zoom room.
Yeah, he just needs to grab it.
Can you please change to the Zoom room here? Thank you. You can see in Zoom?
I can see it in Zoom, yes. Oh, you stop sharing now.
Didn't. How is everyone? How are things? All right. Good.
So next we have Daniel Escudero to talk about sublinear distributed product checks on replicated secret shared data over Z2 to the case space without ring extensions. Take it
Alright.
away.
Thank you so much, Harish. So I'll be trying to be quick on this one so that we can all leave soon. So this is joint work with several great co-authors from different universities. So I invite you to read the paper for more details. I'm going to try to skim over the main points of the paper and the main techniques. So that's what I want to reach towards the end of the goal of this talk. So very quickly, the setting. This talk is going to be mostly about three-party computation, where we're going to have three parties, and they want to compute certain function, and nothing else about the other party's input. And security should hold when the adversary corrupts one party. So we are in the honest majority setting. That's the context of this talk. And more specifically, we're going to consider active security. So why 3PC, three-party computation? I'm going to abbreviate it to 3PC multiple times. So there are multiple reasons to choose this setting. So first is the minimum number of parties you need to get honest majority. So with two parties, you cannot get honest majority. With three parties, you can get honest majority. And that's good because with honest majority, you can get many good properties. You can get a statistical security, you can get guaranteed output delivery, you can get different things that are not possible in this honest majority. And more importantly, and also the reason why, for example, Nishant was telling us earlier about the two-party case with a dealer is that you can get very concretely efficient protocols when you are in this setting. Furthermore, what happens very often is that you don't have three parties. You may have 5, 10, 12, 20, 100. It's very often to consider the case where you have multiple parties and they are going to secret share the data towards three parties. So in a way, three parties are enough if you're okay with this delegated client-server model. Well, there's extensive literature on this type of settings. I'm just listing a few, but this keeps growing and growing and growing. Right? So in MPC, it's common to consider passive security and active security. Passive is that the view of each party leaks nothing about the inputs. Active security, we want to go a bit further. I want to ensure that even if the adversary deviates, it cannot learn anything about the honest party's inputs. So that's what we're going to focus on. And it's also common to distinguish between two types of structures. So most commonly
we use fields, finite fields. They are very nice. They have very good algebraic structure, very good mathematical properties, but they're not that good for representing complex computations, such as the one that appears here frequently, like ReLUs, or let's say, well, comparisons more generally, hyperbolic tangents, approximations, binary computations. It's much harder to represent them with a field than what it is, for example, with a ring of this form. So these type of rings are harder to work with because now they have zero divisors and a lot of other undesired properties, mathematical properties, but they are better for things like PPML. So the setting of this talk specifically is actively secure three-party computation over this ring. So that's what we're going to study in this talk. All right, so let's discuss a little bit what's the cost of active security. Let's say passive security costs this much. How much is active security, which is a stronger notion, going to cost me? How much extra is it going to cost? Okay, so there's a fruitful line of research that had explored the overhead. By the way, we measure efficiency in terms of the number of elements that we need to send, that each party needs to send. That's a good measure of efficiency. In contrast to Nishant's talk, in this type of secret sharing schemes, based constructions, is very common that the bottleneck is communication. So this is a good representation of the efficiency. Okay, and if we take the best passive protocol, it's going to take one element per party, per multiplication. For every multiplication I want to do, I just need to send one ring element or one field element. And thanks to a technique that was recently developed, it was also mentioned before, these distributed zero knowledge techniques. I will refer to them as sublinear checks in this talk. The cost of active is actually one element plus something that vanishes as m grows, where m is going to be the number of multiplications. So because of this state of affairs, we can basically claim that active security costs essentially the same as passive. Because as m grows, this term on the right side is going to be so small that it basically doesn't really affect the term on the left. So that's something we already know. And it holds both for fields and for rings. Okay, but I want to challenge that perspective. I want to really ask if it's true that active security costs the same as passive security. And there are several issues with this type of claims, as usual whenever you have O notation. So first, there are hidden constants. So I cannot tell you on the top of my mind what's the hidden constant here, but it's definitely not negligible. It's like you have to acknowledge it, and if the circuit is not large enough, maybe the extra cost of active security is actually not that small. Moreover, this comes for free, and I keep quoting the for free, in terms of communication, but in terms of computation, is not that cheap. We have to do a lot of extra things locally, each party. In particular, they have to do interpolations on polynomials of certain large degree. The degree is going to depend on the number of multiplications we are operating on. So in practice, the claim that active security comes for free may not be that true. So over fields, there was actually some prior work that has explored the efficiency in concrete settings. So what's the concrete efficiency of active security? Actually implemented it and benchmarked these different protocols. And they found out that indeed these sublinear checks can help in certain conditions. For example, if the network is not super fast, maybe they're useful. If the network is very fast, then you are not communication bounded, now you're computation bounded, and then these sublinear checks are not that good. For example, if the circuit is very deep, it's also useful to have this sublinear check. If it's very deep, we're going to be interacting a lot, and it's very good to minimize the amount of information that we interact on every round. But for rings, for example, like this specific ring of integers 2 to the 64, for instance, we know in theory how to achieve it. We know we can use something called Galois ring extensions, which are the analogous version of Galois field extensions, to get what we want, but it's actually way more expensive than fields. So rings are supposed to be useful because they are like much amenable to comparisons and other type of primitives. But when you have these extensions, they're actually very, very bad in terms of computation. And the hidden constants are even larger than the field case. And there was a huge lack of experimentation on whether this actually can be the same cost as passive. So the question that we ask in this work is, can these sublinear checks over rings be made concretely efficiently? Can we actually make them in such a way that we can claim in practice active security costs the same as passive for rings? So that's the problem we set out to solve in our work. What we managed to show is, yes, there is a protocol, we provide a protocol that has minimal overhead, active security with respect to passive. And the way that we achieve this is by avoiding these Galois ring extensions. We don't have any Galois ring extension in our work, and that's very important. If you're familiar with these things, this is like essentially avoiding Galois field extensions or avoiding interpolation. So that's crucial, and it's actually not that trivial. As a small spoiler, if you look at the zero-knowledge literature, SNARKs and so on, most of them are going to be based on some form of interpolation. And we're going to have to develop some kind of SNARK type of thing because it's sublinear, so succinct. And how do you do that without interpolation? So that's kind of where this is going to. Okay, so we're going to, in one sentence, rely only on random linear combinations. But that says nothing because random linear combinations are everywhere. But if you're familiar with the ring literature, this allows us to apply some of the random linear combination type of theorems we had from previous works. Okay, I do want to give some intuition, or some idea on how we actually get this, but before that, let's get to some numbers. Huge table, huge things, but I want you to focus on a couple of things. So this is our protocol, different number of multiplications. We have more multiplications as we go down. And you can look at the time if you're interested, but what I want you to look at is the factor. So this is what we're going to take as the baseline. And then if we look at this prior protocol, which is the one that has the Galois ring alternative. So let's use Galois ring extensions, and they are for free. They did not implement this. We actually implemented it and found out that it's going to be up to 43 times slower than our protocol if you use Galois ring extensions. We avoid them entirely. So that's a good sign, and this is if you're computation bounded, if you're in the LAN setting. If you're in the WAN setting, then you're not computation bounded anymore. Communication is actually what matters. And in that case, you have more time to compute. So if you're waiting until you send the data, you might as well do some local computation in the meantime. That's why the factor in that case is smaller, but we're still better than them in this setting. And just for reference, I also wanted to share that this is the cost of the passive protocol. So, for example, here we are not that much better than, we are much slower than the passive protocol. The passive protocol is only 13% of our runtime. But if we are in the WAN setting, the passive protocol is 85% of our runtime, meaning the active and the passive protocols are actually very close. Okay, so these are some of the takeaways that I wanted. We have way more like experiments in the paper, so I invite you to check them out. And I do want to jump now into the technique. So for the rest 5 minutes that I have left, I will just focus on techniques. It will be a lot of math, handwritten math, and hopefully we can get somewhat far. All right, so first claim I want to make is enforcing active security in an MPC protocol reduces to checking a dot product. I'm not going to tell you why. Eventually, you have to check a dot product on secret shared data. I'm using this notation whenever you see bracket of something, is that something is secret shared. And I'm writing the modulus here. All right? So it reduces to proving that 3 secret shared vectors, so this is a vector, this is a vector, this is a value, satisfy a dot product relation. That's what checking MPC will reduce to eventually. And it reduces to the case where one party of the 3 parties, let's say the first one, P1, knows the secrets. So trust me on this one, this is a well-known fact on the literature, but of course we show it in the paper. But if you want to prove the correctness of a protocol, you have to essentially resort to a zero-knowledge proof, if you will. You have to prove that a certain secret satisfies a multiplication. That's what it will reduce to. The dimension of this vector is going to be huge. It's going to be the number of multiplications. And the number of dot products, there are many dot products from 1 to n, is going to be proportional to security parameter. Let's say 40 is statistical security parameter, 40, 50, something like this. All right, so this is well known. What is less known, but I'm going to also just state it and not prove it, is that that reduces to proving one single dot product, not n of them, but only one, where the secrets are also around the number of multiplications, but this time the modulus is not exactly to the k, it's to the k plus a little bit more. And this is way less obvious, but it's something that we can enable. And I do have details on the slides, which are going to be made available online, or either you can also check the paper. But this is the first reduction, invisible reduction, that I'm not going to explain how. We now need to prove that one dot product, not n of them, one dot product is correct. So how we're going to do this? We're going to do some dimensionality reduction. And this is a standard step in SNARKs or also in fully linear IOPs, which is a common technique that is also used in these settings. We're going to reduce the dimension of the dot product from big L to small l, which is the original dimension divided by a compression parameter. This is a constant. It's going to be 4, it's going to be 8, it's a concrete constant. Every time we're going to reduce the dimension by a half, eventually we're going to reach dimension 1, and then checking dimension 1 is much easier. So this is already known, okay? This is how these NARCs work. But the key change I'm going to show you in a moment. So the first step is the following. We take the first vector and we're going to split it into blocks. So we're going to split it into blocks of size small l. So small l is very large. Okay, this is still proportional to the number of multiplications divided by 2, perhaps, but still very large. But we have not many blocks. We have maybe 4 of them. Lambda is a constant. So we're going to split this into a constant number of blocks. And then the dot product between A and B can be rewritten as a sum of dot products of the A1 times B1, A2 times B2, A3 times B3. This is a very simple observation. So this is where the magic happens. And it is that we're going to ask P1 to distribute shares of all these intermediary products. So all AI times all BJs, they are a dot product, they're a single element. And we're going to ask P1 to secret share that. How many of them we're going to have? We're going to have a lambda square of them, because we have lambda groups on each and we're taking all possible combinations. And if you're familiar with SNARKs and fully linear IOPs, this is the crucial difference. In fully linear IOPs, Reed-Solomon codes are very special. You take the product of 2 Reed-Solomon codes and you get another Reed-Solomon code with just twice the distance. So if you want to share the combination of 2 Reed-Solomon codes, you only need to share a linear amount of extra terms in terms of the dimension. Here, we're not using Reed-Solomon codes, but it turns out that we're using under the hood a very trivial code whose distance of the square is sort of the square of the distance. Basically, we need to share a square amount of things, but it's a square of a constant, so it's going to be fine. So this is sort of the overview of why does this work and how is it different from previous works. So we are secret sharing these pairwise products. After we do these pairwise products, note that we only take the ones that don't include the index 1, 1. And we do this because the parties already have shares of the claimed dot product. So we can subtract the claimed dot product from the first, from 2 to lambda, and get what is supposed to be the first one. So we don't share the first one, we actually derive it from the previous one. That's how we link the correctness of what we're trying to prove to the new thing that we're proving. And the rest is actually pretty standard in the FLIOP literature. We're just going to take random linear combinations. So we're going to sample random values. We use the Fiat-Schmier transform for this. We can just take the transcript of the previous things and then get random values. We take a random linear combination of these vectors, of the AIs, of the BJs, of the AI and BJ. And the key observation here is that the parties can compute shares of the left side because they have shares of each AI. They can compute shares of the second factor, they have shares of the BJ. And because the dealer, the prover, secret share all these pairwise products, they can also get shares of the right-hand side. And then thanks to this, this is a new dot product. If you look at this, this is exactly a new dot product where this is a single vector. This vector on the left has dimension L. The dimensionality has been reduced by a factor of lambda. And this vector also has dimension L. And this vector as well has dimension L. So we have reduced the dimension from big L to small l with a communication that is only lambda squared. In the prior works, it's going to be a communication proportional to lambda, but this is just proportional. The constants are worse. So ultimately, we end up having better communication. Okay, so as I just wrote, the problem reduces to a new vector, x, y, z, where the dimension is lowercase l. So that's where we get the efficiency. The rest is iterating a logarithmic amount of times, and then eventually you get to a single product, and at that point you can apply the standard technique to check a single multiplication. Okay, so I want to skip just to the end, just to conclude. Intuition on security, we use the speeds to k trick. I cited the paper earlier. Basically, why do we go from k to k plus s? It turns out that if a value is not 0 modulo 2 to the k, and you multiply it by a random value, it's very unlikely that the random value times x is 0 modulo 2 to the k plus s. This is, the over fields is trivial. Random times non-zero is probably non-zero. Over rings, you have to have a little bit of a gap. That's at the heart of it, but the analysis is actually non-trivial because we take a bunch of sums and other things, but that's the heart of it. We have, the paper has many other things, optimization, security analysis, generalization to more than 3 parties. So this works for 4, 5, 6, but still using replicated secret sharing. We have a full-fledged C++ based implementation and way more experiments information, experimental data. So with this, I want to conclude, and thank you so much for your attention.
Any questions?
Please.
The reason why this doesn't work for smarts, is it that the communication is large and that's okay because there's many parties?
Yeah, so the question is why this doesn't work for snarks, and actually maybe it works for snarks. I haven't tried, I would love to try. Like we were focusing specifically on the case of fully linear IOPs, which we didn't frame it as fully linear IOPs, we framed it as distributed checks on secret data, but I have the impression that this could definitely work for snarks. I would love to try that.
You're extending to more parties, like is there is -3?
Yeah, I mentioned this here. So it works for more than 3 parties, but specifically with replicated secret sharing. It doesn't work with Shamir, but not because, well, what doesn't work with Shamir is the reduction to the problem. So you cannot reduce check MPC to the case where there is one prover and this prover knows the secrets. This only works with replicated.
Any other questions? Okay, let's thank the speaker again.
Thank you.
And finally I guess, wait, let's have the slides up first.
Great. Is the microphone working? Yeah, sweet. Just these?
Yes, there's 2. Yep, should try that first. Nope, oh, okay.
Sweet.
Okay.
Take
So
it back.
the last talk of the workshop and the session is Privacy Census Privacy System. Alex is here to give the talk. Take it away.
Yeah, thanks everybody. Today we're going to be talking about a particular use case of privacy preserving ML, in particular census privacy. So this was work done with Stephen Belevin, my master's thesis advisor from Columbia University. And so yeah, why census privacy? So first of all, a census, when a country asks questions to all of their citizens to do an anonymous count for various purposes, is very important. It's useful information that actually goes to really important social programs. That being said, census, the replies are often confidential by law. So here in the US, for example, it's after 72 years that the original data gets released, which introduces a pretty fascinating research question of what privacy preserving technologies can we use to evaluate this information such that we can do what we need to do with the census, while at the same time preserving its privacy. So there are some limitations of this research using traditional privacy preserving methodologies, in particular with noise-based privacy tools like differential privacy, for example, which we'll talk about, you can have some pretty big issues with census data. So someone's age cannot be negative. And if I sample noise from a distribution and an age ends up being negative, that would be a problem. There's other inherent applications of census type data, such as children being older than their parents, which can't reasonably happen. And so it introduces a pretty interesting paradigm of privacy preserving technologies that at the same time need to preserve these axioms of the type of data that's being collected. Similarly, selecting optimal parameters is very difficult. Just getting the slides there. And at the same time, if you want to do research on these censuses, you're going to run into this problem, which is a big focus of this work, that each country's census is going to be very similar, but also very different. So there's some shared abstractions, but also some very unique things about working with censuses. And in general, I think this is one of the most important use cases of privacy preserving technologies. At the same time, the tools for us to experiment with different methodologies simply don't exist. So kind of the state of the art of research software systems for experimenting with privacy and censuses isn't quite there. We don't have the kind of benchmarks that one might expect from a field like this. We cite some of the research there that supports these limitations. And so essentially, we developed a census privacy system here that takes abstractions for many privacy preserving technologies, in particular, differential privacy, which I'm sure everyone here is familiar with, and then also another primitive, which is particularly interesting for censuses, which is synthetic data as a methodology for experimenting with census privacy. And then we also abstracted many countries' censuses, which was frankly the bulk of the work in this system, was finding these country abstractions so that you can apply these privacy tools to any country census that fits this abstraction layer that we developed in the system. It's implemented in Python. We did 5 national censuses and 2 main privacy primitives with synthetic data and differential privacy. Yep. We'll go over this quickly. We've heard quite a few introductions of differential privacy today, but the essential question is, what is the privacy utility trade-off here? We're introducing noise sampled from a statistical distribution to data to make it less representative of the original data, such as Laplacian noise. And then also for synthetic data, we're talking about GANs here in particular. So we have 2 neural networks. One is a discriminator, the other is a generator. And we're essentially trying to map random noise into a distribution that is similar to the underlying data set. And ideally, you get your generator creating something that is eventually statistically indistinguishable from the original data set. So again, we're learning this underlying distribution, but the data is ideally very similar, but also different enough to remain private. Great. So now I'm just going to walk through this software system that we developed and speak a little bit about the design principles which are important for this particular research problem of census privacy. So first and foremost, we wanted to develop something that's modular. You want to be able to introduce any privacy primitive or any census and still be able to use a wide range of tools. So visualizing that data should be agnostic of the country or the primitive, and other types of analysis should similarly be something that doesn't depend on which country you're looking at or which primitive you're trying to evaluate. Yep, so we got some pseudocode here representing that. And the other key aspect here is that we wanted this toolkit to be extensible. And so what that means is that if an organization just wants to implement another country, they should just have to fit one abstraction, and then all the primitives should be applicable. And actually vice versa for different privacy primitives that we want to apply. So there are similar interfaces and abstractions for introducing a new primitive to the toolkit. Yep. Now, to speak particularly to censuses and why developing a benchmark for this use case is actually a bit challenging, but we found some creative solutions, is looking here, we actually have two countries' censuses. One is from the United States, the other is from Australia. And you can see that this information ontology, let's call it, actually overlaps substantially, but still is very different. And so much of the work was developing shared classes that take similar abstractions between this social information, which needs to be kept private, and therefore is, the reason we need to apply these privacy-preserving technologies. But we can find these shared abstractions that actually make it quite usable across many countries. And so in this particular use case, I'd say going from one country to two is rather challenging in finding these abstractions. Going from 2 to 3 and 3 to 4 is, marginally easier every single time. You start to develop these interfaces which actually span most of the questions that these countries are asking. Similarly, I'm going to point out that in this particular census, we have some information which is unique to that one country. And we ran into this quite a few times. Ultimately, the shared interface is a Python datetime object, but there are some unique pieces of information with country censuses that can actually be abstracted. And ultimately, this was a software systems project once we got down to it, and there was quite a bit of data engineering that went into this. We developed classes to generate mock data sets for particular cities. We developed classes that would do quite a bit of data cleaning in order to make sure that there weren't negative ages or children older than parents, for example. And other objects here ultimately made this usable for the particular use case of applying these privacy tools, evaluating their privacy utility trade-offs to the census data. But yeah, ultimately, this was quite a bit of systems engineering that we did here. And then I just want to give an impression of the types of experiments that you can run here. So this is an epsilon accuracy trade-off example based on some of the mock data that we generated. And again, this wasn't necessarily a toolkit to come up with research findings about census privacy in and of themselves, but we wanted to build something that would be very extensible for other researchers to then run more experiments with new primitives and ultimately create more of a benchmark for what we see as a very important use case of privacy and ML here. So yeah, goal is to create the standard benchmark. And what's really nice about this is you can see how the extensibility and the modularity make it so that when you add one more country, for example, you could apply differential privacy to evaluating the accuracy and privacy trade-off of a metric right away. Yeah, in the future, I think adding more privacy primitives in more countries would be very natural. Open sourcing, Dockerizing, and making this more of a production-ready code base that other academics could be using in order to evaluate their benchmarks, as well as adding other countries to make this useful to different organizations that study national censuses would be great. Otherwise, in the PDF here, there's a link to the master's thesis if anybody would like to look further into the work. And yep, that's all I've got. And if anyone has questions, would be happy to answer them.
Any questions? Go ahead.
I'm curious, so the idea is there is like a database and the access to the database is via this API. That would be the idea.
That would be one way to do it. And there are some code bases which have done that. This will actually generate data locally. So the database isn't separate. And it allows you to simulate census data and apply these privacy tools to it to the point that you could evaluate the trade-offs and decision-making around which privacy tool is best, but it's not actually intended to be run on a census's data set, which some of the open source tools that are similar actually want you to run this on a real server of census data. This is more of a benchmarking toolkit, not meant to be run on real census data, but more so meant to evaluate how different privacy tools would affect a given country's census.
Generates similar
You know, it could. In the state that it's in right now, it's meant to be simulations, but yeah, I mean, you could take the same interfaces for these census data sets and actually put yeah, a real Postgres database with an actual census there as well. So that could be a future extension of it. Yes.
Maybe just answer that. Have you run this on 1950 data? It's over 70 years old.
Not yet. That would be a great next step as well. Yeah.
Any other questions? Otherwise, let's thank the speaker again. Okay. Thank all the speakers. Thank you so much. And with that, we bring PPML workshop to a close for its 6th year. There's dinner at 5:30. So I'll see you, some of you at least there. Thank you.